So this short video is going to go over using the ideal gas law to find the molar mass and then ultimately to identify a molecule. And so we're given a problem, and here's the problem shown here, where we're told that the density of a homodiatomic gas was measured at 1.5 atmospheres and 27 degrees Celsius to be 1.95 grams per liter. So using this information, we want to calculate the molar mass of this gas and then ultimately to identify it. So as with any problem, the first thing we need to do is really dissect the problem, figure out what is it asking for, and then to figure out how we're going to get there. And so I'm going to highlight and say calculate the molar mass of this gas. So what we want to find is the molar mass of the gas. So we might recall that when we think about molar mass, the molar mass is the mass of the molecule in grams divided by the moles. So what we need to do is to determine both these things. What is the mass of the gas present and how many moles of the gas are present? And to start off this problem, we're told of a few different things. And what we'll start off looking at is we're told the density of this gas, 1.95 grams per liter. Now, we're not told how much of the gas we have, but we are told this density. And anytime you're confronted with a problem like this, where you're given a density or a concentration, and you're not told how much, one of the things you can do is say, let's just assume we have a certain amount. And in this case, I'm going to try and make the math easier by saying, let's assume we have 1.0 liters of gas. Now, we might not have a liter, but it turns out not to matter because we know this density relationship. If this is true, then that means we have 1.95 grams of gas because we're told the density is 1.95 grams for every 1 liter. If we assume we have 1 liter, then we know we have 1.95 grams. That means we already have the top of our molar mass. This top grams is 1.95 grams. So what's left to do is to calculate the moles. So this is really the problem. How many moles of gas do we have under these conditions? So we're given a pressure, a temperature, and now we have a volume, and we have to find moles. And so what we're going to have to do is we're going to come down here and we're going to use the good old ideal gas law, PV equals N RT. We're going to rearrange it for moles. N is equal to PV over RT. We know the pressure is equal to 1.5 atm. We know the volume we've assumed to be 1.0 liter. And the temperature is 27 degrees Celsius, which we now know we have to add 273 to make that 310 Kelvin. We need our temperature to be in Kelvin. So now we can plug into our equation. And so we have 1.5 atm. We're going to multiply that by our 1.0 liters and then divide by our universal gas constant, 0.08206 liters times atmospheres over moles times Kelvin times our temperature of 310 Kelvin. Our units will cross out, always good to check units. Atmospheres cross off with atmospheres, liters cross off with liters, Kelvin cross off with Kelvin, and we're left with moles. And so we can see the number of moles we get are 0.0609 moles. Now that we have the number of moles, we can come back to this molar mass. And so what we can say is the molar mass, recall, which we have above, molar mass is equal to the mass, which we said was 1.95 grams. divided by our moles, which we just found to be 0.0609 moles. And so the molar mass, if we divide that out, is equal to 32.0 grams per mole. So there is the molar mass of this gas. Now the last thing we have to do is the problem also asks us to identify it. And the key when we go to identify it is this word here. We see this is a homodiatomic molecule. So diatomic means there's going to be two atoms present, and the homo means the two atoms will be the same. So the total molecular mass was 32.0 grams. So if we divide that by 2, we would get the mass of one of the atoms. And so from that, we can find out this has to be the molecule O2. This is molecular oxygen. Thank you.